14.1 Pressure. The outline of this video is as follows. First, we will introduce the fundamental concept of pressure, which describes how a force is distributed over a surface. We will establish the formal definition of pressure as the magnitude of the force acting perpendicular to a surface, divided by the area over which that force acts. Next, we will discuss the standard SI unit for pressure, the Pascal, and see how it is derived from newtons and square meters. Finally, we will work through a concrete example, comparing the pressure exerted by a waterbed to that of a conventional bed with legs. This practical comparison will highlight the crucial role that the contact area plays in determining the resulting pressure on a surface. Let us begin with a fundamental property of fluids at rest, also known as static fluids. The force a static fluid exerts on any submerged surface is always directed perpendicular to that surface. To understand why, recall that solids can resist shearing forces, which are forces parallel to a surface, and tensile forces, which pull an object apart. Fluids, by their very nature, cannot sustain these types of stresses. If you try to apply a shearing force to water, its layers will simply slide past one another. Because a static fluid cannot support a force parallel to a surface, the only force it can exert must be entirely perpendicular to that surface. This force is always compressive, meaning it pushes inward on the object from all sides. For example, if you submerge a ball in water, the force from the water at any point on the ball's surface points directly toward the ball's center. The key takeaway is that forces from a static fluid are always compressive and act at right angles to the surface of any object within it. Let us now formally define pressure, which is the key quantity for understanding how static fluids exert forces. Pressure, represented by the capital letter P, is defined as the magnitude of the force acting perpendicular to a surface, divided by the area of that surface. This gives us the equation P equals F divided by A. A crucial point to understand is the distinction between pressure and force. Pressure itself is a scalar quantity. This means it has only a magnitude, like temperature or mass, and no direction associated with it. However, the force that this pressure exerts on any surface is a vector. As we saw with the submerged object, this force is always directed perpendicular to that surface. We can measure pressure using a simple device like the one shown, which uses a piston and a calibrated spring. The fluid pushes on the piston, and the spring's compression indicates the force. Knowing the piston's area allows us to calculate the pressure. The key takeaway is that a scalar pressure at a point in a fluid generates a perpendicular vector force on any surface it contacts. This slide clarifies the relationship between force and pressure, especially when pressure is not constant. First, let us address a common point of confusion. Pressure is a scalar, meaning it has no direction. The force resulting from pressure, however, is a vector, and it always acts perpendicular to the surface. When pressure varies across a surface, we cannot simply multiply pressure by the total area. Instead, we must use calculus. We consider the tiny force, dF, on an infinitesimally small area, dA. This force element is equal to the pressure P at that location times the area dA. To find the total force on the entire surface, we must sum up all these tiny force elements by integrating. Therefore, the total force F is the integral of PdA over the surface. For example, the force on a dam is calculated this way because water pressure increases with depth of. In short, when pressure is not uniform, you must integrate it over the area to find the total force. Now that we have a mathematical definition for pressure, let us establish its standard units and build some physical intuition for the concept. In the SI system, the unit for pressure comes directly from its definition of force per unit area, giving us newtons per square meter. This unit is given a special name, the Pascal, abbreviated as PA. So 1 Pascal is exactly equal to 1 Newton of force distributed over an area of 1 square meter. To feel the difference between force and pressure, imagine pressing a thumbtack between your thumb and forefinger. Your thumb is on the sharp point, and your forefinger is on the flat head. The force exerted on your thumb is equal in magnitude to the force on your forefinger. However, the tiny area of the tack's point concentrates that force, creating a very high pressure on your thumb. In contrast, the much larger area of the head results in a low, comfortable pressure on your forefingers. This simple demonstration shows that for the same applied force, a smaller area results in a much greater pressure. Let us apply our understanding of pressure with a quick conceptual question. Suppose someone accidentally steps on your foot. Who would you rather it be? A large basketball player wearing sneakers, or a petite woman wearing spike-heeled shoes? While the basketball player has a much larger weight and therefore exerts a greater force, the key is the area of contact. The woman's spike heel concentrates her entire body weight onto an extremely small point. In contrast, the basketball player's sneaker distributes his larger weight over a much larger area. Since pressure is force divided by area, the tiny area of the spike heel results in a tremendously high and dangerous pressure. You would be much better off being stepped on by the basketball player, because the lower pressure from the sneaker is far more manageable. Let us begin with a practical example to connect the concept of density to the force of weight. We will calculate the total weight of the water inside a typical waterbed mattress. The problem provides the dimensions: 2 meters long, 2 meters wide, and 0.3 meters deep. Our first step is to calculate the volume by multiplying these three dimensions together. This gives us a total volume of 1.20 cubic meters. Next, we use the definition of density to find the mass of the water. Since mass is equal to density times volume, we multiply the density of water, which is about 1,000 kilograms per cubic meter, by our calculated volume. This gives us a mass of 1,200 kilograms. Finally, to find the weight, we multiply this mass by g, the acceleration due to gravity. Using 9.80 meters per second squared for g, we arrive at the final result. The weight of the water is 1.18 times 10 to the power of 4 newtons. This is a very large force, roughly 2,650 pounds, and demonstrates how a simple density calculation can have important real-world implications. Now that we have the weight of the water, we can find the pressure it exerts on the floor. Pressure is defined as the force applied perpendicular to a surface, divided by the area over which the force is distributed. In this case, the force is the weight of the water, which we found to be 1.18 times 10 to the power of 4 newtons. The problem specifies that the entire bottom of the waterbed is in contact with the floor. Since the bed is 2 meters long and 2 meters wide, the contact area is 4 square meters. To find the pressure, we divide the force by the area. This gives a result of 2.94 times 10 to the power of 3 pascals. Although the waterbed is quite heavy, its weight is spread over a large surface. The key takeaway is that the pressure depends on both the magnitude of the force and the area of application. Let us now consider a follow-up question that highlights the crucial role of area in the definition of pressure. What if we replace the heavy waterbed with a much lighter, 300-pound regular bed supported by 4 small legs? First, we find the force, which is the bed's weight. We convert 300 pounds into standard units, which is approximately 1333 newtons. Next, we calculate the total contact area. The weight is supported by 4 circular legs, each with a radius of 2 centimeters. The area of one leg is pi times the radius squared. Multiplying by 4 gives a total contact area of only about 5 times 10 to the power of -3 square meters. Finally, we find the pressure by dividing the force by this very small area. The result is a surprisingly large pressure of 2.65 times 10 to the power of 5 pascals. Even though the regular bed is much lighter, it exerts almost 100 times more pressure than the waterbed, because its weight is concentrated on the tiny tips of its legs. Let us summarize the fundamental concept of pressure. We have defined pressure as the amount of force applied perpendicularly to a surface, divided by the area over which that force is distributed. This relationship is expressed by the equation P equals F over A. It is important to remember that pressure itself is a scalar quantity, meaning it has only magnitude. The force associated with pressure, however, is a vector that always acts at a right angle to the surface. The standard international unit for pressure is the pascal, where 1 pascal is equal to a force of 1 newton spread over an area of 1 square meter. This principle explains many real-world phenomena, like why a sharp knife cuts so well. It concentrates the force onto a very small area, creating a very high pressure. The essential takeaway is that for a constant force, decreasing the area of application increases the pressure. Let us pause to review the key ideas with these two questions. The first question asks you to explain why the force from a static fluid must be perpendicular to any surface it touches. To answer this, recall the definition of a static fluid, which is a fluid that is not flowing. If a component of the force were parallel to the surface, it would act as a shear stress. What would this parallel force cause the fluid molecules to do? This would cause the fluid to flow, which contradicts the condition that the fluid is static. For the second question, start with the definition of pressure, which is force divided by area. Both the cube and the sphere have the same mass, so they exert the same downward force on the table due to gravity. Therefore, the difference in pressure must come from the area over which this force is applied. Consider the shape of the contact area for a cube resting on its face versus a sphere resting on the table. The object with the smaller contact area will exert the greater average pressure.